In today's video, we're going to look at exponential and logarithmic models. This is where we use either an exponential or a logarithmic function in order to model what's happening in a real-world situation. I'm going to go through the textbook examples for these just because there's only a couple things in here and these examples are really good, and then we can extend this in our homework problems. But what I want to look at first is these exponential models. So let's say I have a function of this form here. P of t is equal to p0 e to the kt. What this does is it tells me at time t how much or whatever the value of my function is at that particular time. Okay, p0 is what happens at time t is equal to 0. Why is that? Well, let's think about p of 0. Okay, if I plug in t is equal to 0, so what happens at time 0? E to the power of kt would be e to the power 0. Anything to the power 0 is 1, so I would end up with p0 times 1, which is just p0. So p0 is my initial value. It's how much I have of something at time t is equal to 0, so how much I start with. K just determines the rate of growth. Okay. What we want to look at is whether k is positive or negative. If k is positive, then I end up with e to a positive power. That means it's going to get larger and larger and larger as t gets larger and larger. Okay, so that means that I end up with this model where I have a growth function because it's going to get larger and larger and larger as t grows. If k is negative, then I end up with a situation that as t gets larger, e to the power of kt is going to be e to the power of a larger and larger and larger negative number. Now remember, when I have e to the power of a negative number, it's the same thing as doing 1 over e to the power of its positive counterpart. Okay, so that means that as t gets larger when k is negative, I end up with 1 divided by a larger and larger and larger number. So 1 divided by a number that gets larger and larger means that I end up with a value that gets smaller, which gives me a decay model. So whenever k is positive, I have a growth function. And whenever k is negative, I end up with a decay function because it's going to get smaller as time increases. And it's all to do with whether k is positive or negative and what happens to the function in that case. Let's go ahead and look at our first example. So this is looking at the pressure on an object exerted by the atmospheric pressure, okay? And as the height of the object increases, we see that its atmospheric pressure decreases, okay? Again, we're looking at a decay function. K is negative in this situation. So as our height, h, increases, our atmospheric pressure, our overall function, is going to decrease. Okay, so as h increases, because that k value is negative, I've got a decay function, so my overall function value is going to decrease. H is going to be in kilometers above sea level. Okay, so the first thing they want to know is find the atmospheric pressure on an object at a height of 1.5 kilometers above sea level. So in this case, H is going to be 1.5. You can plug this straight into a calculator. You have the value E, that constant, on your calculator, and you're going to do e to the power of negative 0.145 multiplied by that value of h, 1.5. And then at the end, you're going to multiply that by 760 to give you 611.4410. Okay. Notice we do have this 760 out the front. If I was to plug in h is equal to 0, then I would end up with my pressure at height 0 is 760. Okay, so that is what my pressure is when I am at sea level, when I am 0 kilometers above sea level, that is my pressure. And we have seen that when I go up 1.5 kilometers, then it means that my atmospheric pressure has dropped. Again, showing a decay function, because I started at 760 and now that I've gone up 1.5 kilometers, my pressure has dropped to 611. Okay. The next part of the problem says to find the atmospheric pressure on an object at a height of 10 kilometers above sea level. Okay. Again, this is the same thing as before. There is a typo here. That should be 10, not 1.5. They've plugged in h is equal to 10, so I'm looking at what happens at 10 kilometers above sea level, and I get 178.2734. So again, you will plug that into your calculator. E to the power of negative 0.145 multiplied by 10, and then we multiply that by 760. And again, as we have gone up, so h has increased, our function value has decreased because we have a negative value of k, meaning I have a decay model here. So as h increases, we have a decrease in our function value. In our next example, we're looking at the price of a Toyota Prius that is T years old. Again, there was a typo here, so I've quickly erased it to be exactly what it should be. But we have the price at time t is going to be 22,500 multiplied by 0.89 to the power t. Okay. In this case, we are looking at an exponential function where I have got a different base to e. So this is an exponential model of the form b multiplied by a to the x. So it's slightly different to what we were looking at before. But it's the same idea. We're just going to be plugging in values. It says, how much does a 1-year-old Toyota Prius cost? We're looking at t being in years, so I just plug in t is equal to 1. Let's think about what we expect here. Okay, a is between 0 and 1. Okay, a is 0.89. If we look back at our graph, for the exponential functions where a is between 0 and 1, I would expect this to be a decay model. Okay, if you go back and look at what we did when we had those graphs, you would expect this to be a decay model. As that value of x, or in this case t, increases, you're going to get that your function value will decrease. Think about it in terms of the problem. That makes sense. We have a car here. The older the car gets, the cheaper it's going to get. So I should get a decay model here. And when we plugged in that value of t is equal to 1, I end up with $20,025, which makes sense again. Look at our value of P0. Okay, when t is equal to 0, so at time 0, the car was worth 22,500. Okay, that's how much the car was when it was driven off the lot. After a year, it's worth $20,025. Okay, so again, the price of the car has dropped. So this problem is slightly different to what we had at the start, but it still models what we would call a decay model. Okay, it's still a decay function because we have that base value being between 0 and 1, and when we look at the graph for an exponential function where that base is between 0 and 1, we still have a decay function that as the power of a increases, then the whole function itself decreases, which makes sense with what we're looking at here with the price of a car. Okay, the next one says, how much does an 18-month-old Toyota Prius cost? Again, be very careful when you do this. Remember, t is in years, so 18 months is 1.5 years, so we plug in t is 1.5 and we get $18,891.55. Again, the older the car gets, the less it's worth. So this makes sense with the real world problem as well as with the function. So please keep that in mind when you do these. The next type of model that you may see is a logarithmic model. These don't come up as often in this course. We look more at logarithmic equations, as you'll see in section 15. but they are still used in a lot of real world problems. So I do want to go over an example of it. A logarithmic model is of this form c multiplied by log base a of x. So c is just the value at the front. It's the coefficient. It's going to be a constant. Then we have log base a. A is going to be another constant. It's the base of our logarithmic function. And x is our argument. That's going to be our variable. Then what we're going to look at is this particular example here. Okay, I've got a function here, and it's used to determine the magnitude of an earthquake when compared to the value I0. That is the baseline measurement of the movement of the Earth's crust. So I0 is just how much movement you get on a day-to-day basis of the Earth's crust. Okay, the magnitude of the earthquake is how much above that, how many times that do we have of this movement. Okay, so we're looking at the magnitude of the movement compared to that value I0, and it's done by using this log function. Okay, our value c at the front that we had here is just 1. Okay, our coefficient of our log function is 1, and then our base here we had log base a. Well, here we've just got log of this. That means we have log base 10. Remember that that is our common log function. So it's log base 10 whenever they just write log. And then our argument here is I over I0. I is our variable, and I0 is just how much we have of this movement on a day-to-day basis. So to determine the magnitude of an earthquake that has intensity of 100 times I0. So this time our magnitude here is going to be determined by looking at this intensity that is 100 times our normal level of movement of the Earth's crust. Okay, so I'm going to plug in I is equal to 100 I0. Okay, when I plug that in, I'm going to get this cancellation of I0s happen, and I end up with log base 10 of 100. So that's asking, what power do I raise 10 to get 100? Well, obviously 10 squared is 100, so my answer is 2. So that tells me that the magnitude of the earthquake is a 2. This time I'm looking at the magnitude of an earthquake that has intensity of 1 million I0. So I substitute that into my equation. And now I've got log base 10 of 1 million. So it's asking what power do I raise 10 to get 1 million, which is 6. So in this case, the magnitude of my earthquake is 6, because I ended up with the intensity of this movement of the crust was 1 million times my standard level, which gives me a magnitude 6 earthquake. So like I said, you do see this a lot in real world problems, so I wanted to go through one quick example of this. In our next video, we're going to start looking at the properties of some of these log functions, which will help us in some of these situations if you ever come across these logarithmic models.